Hello and welcome to Disseminate the Computer Science Research Podcast. I'm your host, Jack Wardby. A reminder, if you enjoy the show, please consider supporting us through buying me a coffee. It really helps us keep making this show. Today, I'm pleased to say I'm joined by Tarikul Islam Papon, who will be telling us everything we need to know about his recent paper, Acing the Bufferpool Management Paradigm for Modern Storage Devices. Papon is a PhD student at Boston University. So I'll give you a very short introduction there, Papon, but maybe you can tell us a little bit more about yourself and how you became interested in data management research.
Hi, Jack. Thanks for the introduction, and I'm really happy to be here. So as you have already said, I'm a PhD candidate at Boston University. I started in 2019. Here, before my PhD, I worked as a lecturer in Bangladesh, where I completed my bachelor's and master's. There, I served as a lecturer for 4 years. And during my master's, I got involved with like a couple of projects that involved handling large amount of data. So through that, one of them was actually to find like the most influential node in a social network. So there we had to crawl billions of nodes, and eventually we had to handle a large amount of data. So from there, I kind of grew that fascination toward data management, and eventually decided to do my doctorate over here.
Fantastic stuff. So yeah, today we're going to be talking about secondary storage devices and Bufferpool managers. So maybe we can take one of those at a time and start off by telling us about hard disk drives and solid state drives and what they are and how they differ.
Yeah. So, I mean, for the last couple of years, I've been working on this domain of how to actually build better data systems for modern storage devices. So by modern storage devices, I mean solid state drives. So if we take a look at like the landscape of the storage devices, it has changed like quite dramatically over the last 3-4 decades. Like from tape, we moved to hard disk. Hard disk has been like the dominating device. And like the last couple of decades, SSDs or solid state drives, they have taken the place of hard disks, or they are slowly taking the place of hard disks. So like if we want to like talk about the fundamental differences or the fundamental properties of these two types of devices, hard disks are mechanical devices. There are few rotating platters. There is a head that moves. And because of these mechanical components, there is kind of like a restriction how fast you can actually access data from hard disks. And also random access are slower because of this movement. Sequential access can be faster. And in contrast to like all of these, SSDs are purely electrical device. So they store data in chips, and they kind of adopt a very hierarchical structure, which allows them to perform concurrent IOs. Like you can do multiple reads and writes parallelly, which hard disks do not allow you to do that. And so because of the adoption of this electrical device and also the hierarchical architecture, SSDs have fast random access and also quite fast sequential access as well. And one like key bottleneck or key challenge of SSDs is you can only write a limited amount of times in an SSD. So every time you are writing, you are slowly destroying the cells a little bit. So it kind of puts a maximum limit of how many writes you can perform on the disk. And writes are slightly slower than writes can be up to 1 order of magnitude or maybe up to 10 times slower than reads. It varies across devices, and writes are slightly slower than reads. So essentially, these are the basic differences between these two types of devices.
Awesome. Yeah, just out of interest there, you said that every time you write to an SSD, you destroy it a little bit, and that's kind of a permanent thing. How long, if we've got a really write intensive, maybe we can talk about this later on, but a really write intensive sort of workload, how long will my SSD last?
So yeah, this is a very good question, and the answer is actually it depends like what kind of SSDs that you are using, obviously. But for a normal consumer, for a regular consumer, I guess it will last around 5 to 10 years with heavy write extensive environment. And yes, as you can see, like most people will not actually realize this issue. So this is an issue, and obviously when you want to develop something for SSDs, you need to keep this in mind. But at the same time, like most people will never really actually realize this issue, because the number of writes you can do, it is not too small, so it's quite big actually.
Yeah, like the most users won't rub up against that sort of extreme. That's a good point. Cool. So that's one half of the story today. So then the second half is these Bufferpool managers, and can you maybe tell us a little bit more about kind of what a Bufferpool manager is and what role it plays in a database?
So essentially, like most of the problem of the data management community comes from the fact that secondary storage devices are slower than main memory. So that is kind of like the fundamental bottleneck that where we're at. So when you have a database, if the database is stored in your storage device and you need to access the database, so what most database systems does is that it kind of keeps a small memory in the small set of pages. It keeps track of small set of pages in the main memory. So that works like a buffer. So what is the purpose of this buffer? It keeps track of let's say, most frequently accessed pages, or the pages that are being most frequently being accessed. It keeps track of them so that you do not have to go to the storage devices to access them. That is essentially the purpose of the buffer pool for a database, for a DBMS or a database management system. Now, the most research actually focus on developing the scheduling policy for this buffer pool, like which pages to keep in the buffer pool. That has been like a very active area of research, and many algorithms like LRU, least recently used, least frequently used, and a lot of algorithm clock and so on have emerged. And there has been like new policies for specifically flash devices, which try to minimize the number of writes, because SSDs suffer from that write endurance problem. We kind of wanted to tackle this problem from a different perspective. We did not want to modify the page replacement policy. Rather, we wanted to see if we can actually use the device's internal properties to get the most benefit out of the devices. So by utilizing the device more, you can use this with any page replacement policy. And we wanted to see that how we can make the buffer pool faster. And if the buffer pool is fast, the whole database performance is actually affected through that.
Amazing. That kind of, I guess, preempts my next question. As I say, can you give us the elevator pitch for ACE? But I guess that's it. It's like, rather than changing the algorithm we use to kind of move pages in and out of the buffer pool, it's more how can we exploit and kind of co-design this system with the hardware to kind of to make better use of the actual properties of the underlying hardware, right?
Yes, exactly. You kind of summarized it very well.
So kind of just linking that back to kind of, you mentioned a few sort of algorithms have been designed for like Flash and other things. What are, I mean, there's two sort of challenges and shortcomings you identify in your paper of these existing Bufferpool managers. Can you maybe elaborate on what these are a little bit more?
Yeah. So most of these approaches, what they try to do is that, first of all, they always read and like they exchange one page for one, they can exchange one write for one read. So for example, when you want to evict a page from the buffer pool, and if that page is actually a dirty page, so you have to clean it. By dirty, I mean that there has been updates applied on that page, and when you are flushing it, you need to apply those changes permanently in your storage devices. So you have to write it, and it is very possible that probably the request that caused this eviction is a read request. So you are essentially exchanging one read for one write. And none of these approaches, or none of the as far as we know, none of these approaches actually take into account the device concurrency. So you can actually, they always evict one page from the buffer pool and read one page. Can we write multiple pages from the buffer pool? That was the question that we initially started, that can we write multiple pages concurrently so that we can clean most of the pages, and then the next request will be mostly for clean pages, and there will be spaces in the buffer pool since you have already written back multiple pages. So that's kind of what started the whole idea.
Kind of with these challenges in mind then, and when you were kind of trying to answer this question and starting to work in this sort of space, you kind of, I'm guessing somewhere on there, you kind of, okay, we want to refactor the buffer pool design space. I guess this maybe happened at the start when you're trying to get a grasp of what's out there and how we could do this. So can you maybe tell us about this refactored design space you came up with? what it looks like, and then how did it go about influencing how you designed ACE?
So just to summarize that, like the major two challenges of state-of-the-art systems are essentially they do not consider the asymmetry of the device. So writes are slower than read. You need to consider this, and also the main power of modern storage devices, that is concurrency, that you can actually perform concurrent IOs. These systems do not take into account that. So we kind of ask the question, and one other key thing, like this is kind of associated with these two challenges, is that when you are writing, when the writing and eviction are two different steps, but essentially all these approaches, they kind of take like these two decisions based on one decision, and that is the page replacement policy, like which page needs to be evicted. If the page is dirty, then you write it back. So there is no separation between like the eviction and also the write back. So we wanted to ask that it can, by decoupling these two design decisions, and that is which pages to be written back and which pages to be evicted, can we do something, and also can we evict multiple pages? So we kind of drew a new bufferpool design space, and we listed these questions: that can we write more pages concurrently, can we evict multiple pages from the bufferpool? If so, can we prefetch multiple pages so that the performance can be impacted? So overall, in the design space, there are like four major components. That is the eviction policy, and it includes the page replacement algorithm, and along with the design decision that how many pages to be evicted from the buffer pool. And then there is the component of writer, and the writer component decides how many pages to be written back concurrently. And we always decide to write multiple pages, since devices can support concurrent IOs. And the other component is the reader, and the reader essentially is a prefetcher, and we have tested with two prefetcher, but any prefetcher can be integrated. And honestly, in our experiments, we did not find prefetching to be that effective, because it heavily depends on the workload characteristics. But yeah, you can, I mean, if you know that the workload has a predictive pattern, then it helps. So we have also seen that. So yeah, with all these, that is kind of like the refactor design space, where we split up the eviction from the write back.
Awesome. Yeah, that makes total sense. Cool. So I guess kind of with that then, tell us how ACE works.
So the primary idea of ACE is pretty simple. That is, every time you need to write back a page, you write multiple pages. And how many pages do you write? You write based on the device's concurrency. So now I will talk a little bit about what the device concurrency means. So we experimented with several SSDs, and we found that every device has like a sweet concurrency point, and this actually varies from read request from write request. So for write requests, most SSDs have a concurrency value of around 8 to 25. It depends based on the devices. So let's say if the write concurrency is 8, that means that you can actually issue 8 IOs at the cost of one IO. Almost at the cost of one IO. It should not be like it is not exactly one IO, but the increase in the latency is not that significant. And the main thing is that when you are issuing these 8 IOs, you get to utilize the full bandwidth of the device. That is where the main benefit comes from. So a device that can support, let's say, 30 megabyte per second for one IO, it can give you up until 240 Mbps or something like this. It might not be exactly linear, but it can give you almost 8x or 6x throughput. So by using that concurrency value, that sweet spot, that write concurrency value, ACE decides how many pages to write back. And if the prefetching is enabled, then ACE also evicts multiple pages from the buffer pool, and this way it clears up the space, and that space is filled up by the prefetcher. And the choices are different for the pages to be written back and the pages to be evicted, in the sense that the pages that are being written back, those are always dirty pages, and the pages that are being evicted, that is driven by the page replacement policy. So it will just evict the last 8 pages from the buffer pool, or X pages from the buffer pool.
So I just wanted to touch on that. You said that there's a sweet spot in the concurrency. So my question is, how you determine that? Is it sort of based on like the hardware characteristics? So it's a sense of like, I know I've got this spec of SSD basically, and I can say, okay, this pretty much it's around 8, whereas this brand is around like, I don't know, 20. Or is it more? Could you get a lot of variability kind of within brands? Yeah, what's the
Excellent question.
variability like?
So yeah.
Yeah.
Yeah, this is a very good question. So to know the exact, like very exact value of the write concurrency, what you should do is perform a benchmarking. There you try to do a stress test performance using like varying the number of IOs of the device and computing or calculating the bandwidth or the throughput that you are achieving. That is like the best way to do it. But if you, let's say, you don't know like which tool to use, or for this specific example, you only have the specs of the SSDs, you can almost blindly use the number of channels of the device, like the number of channels the SSD has. This can be very close to the sweet write concurrency of the device, or the optimal write concurrency of the device, but not necessarily the exact value. But it will give you a very close estimate of the value.
Yeah, you'll be in the right ballpark, right? So
Yeah,
if the true value is 10, you're picking 11 rather than picking 20, right? I guess.
yeah.
Cool. So I mean, obviously, you mentioned earlier on going about that this like SSD sort of like degrade over time. Does that mean that the sweet spot is also changing over time as well?
That is actually a very good question, and I will test it out. That's what I will say. So the thing is, to test it out, you really need to run it for very long amount of time. So I have been working on these devices for like 1.5 years, and I haven't really, even very recently, I actually performed an experiment, and I did not see any degradation of these devices. So the device's write endurance might, so I mean, this is only my hypothesis. So the
Sure.
device's write endurance might not actually affect the bandwidth or the read write concurrency. So you can write probably, let's say, 1 billion times in an SSD cell. But every time you are writing, you will get almost like very close to that bandwidth that you would have achieved from the devices. So I don't think it directly affects it, but yeah, it is a possibility. And to do that, we need to actually test the value for a longer period of time to actually see what is happening with it.
So before we go any further, actually, I just wanted to kind of ask, what does ACE stand for? It's an acronym, right? So I kind of
Yeah,
what's the
yeah.
meaning behind it?
The acronym stands for Asymmetry Concurrency Aware Bufferpool. So it kind of takes into account the two key properties of SSDs, that is read-write asymmetry, writes are slower than reads, and the concurrency, that SSDs can perform concurrent. So from that, it came to become ACE.
Nice. It's a catchy acronym. It's a good name.
Yeah,
Cool.
thanks, Leo. I'm glad that you like it.
So we're talking about implementation there. So I know for the experiments in your paper, you implemented ACE in Postgres. So
Yeah.
I'm interested to know kind of more about that experience and how difficult it was dealing with kind of, I'm guessing, quite a large and old code base. And yeah, tell us a little bit more about the implementation effort.
Yeah, the implementation effort was heavy, but the thing is, we did not really change most stuffs of the DBMS. Like in Postgres, most of our changes were focused in the storage region and very specifically in the buffer pool. And we needed to implement some low-level primer that could actually use the concurrent IOs of the devices. So we needed to write some libraries to get them. And yeah, the benefit of ACE is that so to test this, we had to implement several page replacement policies in Postgres, and the implementation of the page replacement policies, like we tested with four LRU, CF LRU. CF LRU stands for clean first LRU, And there is also another variant of LRU, that is LRU WSR, and also the clock sweep, which is the default page replacement policy of Postgres. So we implemented all these page replacement policies, but these were totally independent of like the actual implementation of ACE. So that is essentially the beauty of ACE, that you don't really need to change the replacement policy, but it is kind of like a wrapper that sits on top of these policies and decides like how many pages to write, and writes them concurrently, and evicts them if required.
How easy would it be to take the existing implementation and port it to a different database system?
So mostly it will require some software engineering effort, not more than that. So it will not. I mean, what I'm trying to say is that it will not take too much effort from the perspective, because the idea you can actually port it very easily. That you need to write the change is minimal. That you need to write multiple pages at the same time, and you decide the eviction based on the page replacement policy. And this very simple idea can give you good performance benefit, because you are utilizing the device more. You are getting more utilization from the device. That is so. Yeah.
So I guess let's talk some results then. So can you maybe tell us about your experimental setup and the experiments and how you went about evaluating these?
So we evaluated ACE. We implemented it in our server, and our server has a very it is a very powerful machine with 384 gigs of main memory and everything. We implemented ACE in Postgres and evaluated with the standard TPCC benchmark, and also we created some synthetic traces just to stress test ACE for different scenarios. So just to summarize the results, when the workload contains more writes, ACE performs more, because the main benefit of ACE comes from like concurrent writing or efficient writing. So when the workload has more writes, the benefit of ACE is more. It can be as high as up to, like in our experiments, we found that it can be up to 2x. You can gain in some cases when there is for write-only workloads. For as you reduce the number of writes in the workload, the performance, performance benefit reduces, but you can still gain benefit. Like we tested with 90% reads and 10% write, which is a very read-intensive workload, and we found out that it still be like 20%, up to 15% to 20% faster. And also for read-heavy workload, if the workload has a predictive pattern, the performance benefit increases slightly. And we also experimented with the TPCC benchmark. And in the TPCC benchmark consists of 5 transactions, and each transaction has different properties. So we saw that the write-heavy transaction had the most benefit of I don't remember the exact number, but I think it was 1.5x, and the mixed transactions had a benefit of 1.3x and something, and the read-only transactions did not have any benefit. So the main takeaway from these experiments, what I would say, is that even if the workload has a very small amount of write, ACE can gain benefit from you. But if there is no write, it is fine. It will, because then is just converts to a very classic Bufferpool manager. So no performance penalty at all. But if the workload has even a very small portion of write, you will gain some benefit by adopting this idea. And very interestingly, we observed that we performed the experiment across multiple devices, and we saw that the device that has the highest asymmetry, that is the device where write is the slowest compared to reads, in those devices has the highest performance benefit. And the reason behind this is essentially since in those devices writes are more expensive, if you can perform efficient writing, or if you can perform concurrent writing, then you get to amortize the expensive write cost, and that gives you the more speed up in those devices.
So a few questions from me fall out of that there. So in the asymmetry there between the read and the write forms, is it higher end SSDs that have is there any correlation between the sort of the cost of the SSD and the asymmetry, or is it kind of the cheaper ones have are all over the place, and you've got a big disparity between read and write performance, whereas it's more sort of even for higher end? Or is there no sort of cost there? I'm kind of maybe touch on the cost implications maybe a little bit.
Yeah, good question. So there is no direct comparison or no direct correlation between the cost and the read rate asymmetry, as far as I know. The thing is, some SSDs, they are read intensive, and the read intensive SSDs tend to have a higher read rate asymmetry. And it can be a very fast, like the reads can be very fast and the device can be expensive and everything, but the read rate asymmetry can be let's say 10 or something like this. Whereas there can be devices, like there can be very low end devices which has nominal read rate asymmetry like 2 or 3 or something like this. So it does not really directly depend on the cost, rather the specifics, like the internals of the device, and yeah, what you want to get from the device when designing it.
This is great. It sounds like almost like a free lunch, right? So does the wrapper layer introduce no sort of overhead at all? Like it's totally negligible. Non-negligible is because I guess there must be some sort of computation happening there to kind of determine what should happen next. But that's very minimal, is it?
Yeah, so when you are using concurrent IOs, and when you can actually write multiple IOs, and at the cost of a single IO, you can get the benefit. And it is not really a single IO, as I have already mentioned. There is a penalty, but the penalty is not like the exact number of the number of the IOs. So you can gain by adopting this very simple idea. You can actually gain some performance benefit, and there is a catch. The catch is again almost negligible, since ACE writes a bit more aggressively. Since you are writing more, like every time you need to write back one page, you are writing writing, let's say, 8 pages. Since you are writing a bit more, in our experiments we observed that this value remains between 0.1%, like the increase remains between 0.1%. You might think that, okay, it should have been much more because S is writing more pages, but more pages at one go. But that's not the case, because since when you have written back multiple pages, the pages has been cleaned. So the next evictions will be actually free of cost. So the next evictions, you will just evict clean pages. So evicting a clean page from the buffer pool is not an operation. You just drop it from the buffer pool. You just forget about it. So ACE writes beforehand, like it writes preemptively, but in the long run, it almost gets amortized over time, and the increase in write remains between 0.1%, which is almost negligible.
So if you, as kind of said, there's no sort of scenarios at the moment. Obviously, where it's very dependent on the workload, but where kind of ACE's performance is kind of suboptimal, or like, I guess, are there any other limitations of ACE at the moment?
As far as as far as we know, that the write endurance and the slight increase in write amplification, that is essentially the penalty of ACE. Other than that, even the workload, if contains a little bit of write, then ACE will have performance benefit. The concept of ACE will have performance benefit, and the idea is very simple, but you can actually get decent benefits. So that is that is kind of like the beauty of this idea, and we kind of feel that this way. And like during our submission process, we have actually seen that sometimes, some people can actually understand that, yeah, okay, this is a very simple idea, and how is it novel, and this is kind of like an engineering effort. So you kind of get this, but eventually, as we kind of evolved and refactored the buffer pool design space, and after adding the prefetcher, then we kind of got the satisfaction of what we wanted to actually build. So yeah, even with this simple idea, you can get good benefit.
Yeah, I mean, there's beauty in simplicity, right? Like something doesn't have to be super complicated to kind of the worth of something and the quality of an idea is not linked to its complexity, right? So the fact that it's simple, it works really well, and it is ACE, like it lives up to its name and gives you pretty much good performance in like almost every scenario. is like is fantastic, for sure.
Yeah.
Cool. So I guess on that kind of, where do you go next then? So is it kind of, can we exploit different types of hardware, or yeah, what's the next steps with ACE?
So, like now, what we are working on is that we are trying to import this idea of asymmetry and concurrency in different aspects of data management. So, very recently, we have worked on developing a graph database, or like a graph manager that can utilize the concurrent I/O and can implement some algorithms. So that is one aspect. We also want to work a little bit on, as you probably know, that our lab works a lot on LSM trees and log structure merge trees. So we want to import this idea of asymmetry and concurrency into LSM compactions and see how they can benefit. So yeah, the buffer pool was just one example of this idea of asymmetry concurrency aware storage like system design, and you can adopt this idea into multiple different applications and see the benefit.
Nice little plug there for Suvadeep's episode on LSM tree, so yeah, the listener can go and check that out as well. Cool, but yeah, no. So on that also, I mean, I can imagine some hypothetical scenario where, I don't know, I'm running my database in the cloud, and all of a sudden I want to change the underlying hardware that it's running on, and I want to move from, I don't know, SSDs to some other sort of cool new storage device that my cloud provider is offering me. Do you think it'd be possible to kind of have that wrapper, like almost be intelligent enough to say, okay, well, the hardware's changed now, so I need to change what I'm doing to give better recommendations, essentially, of what I can write out, or what I should prefetch, for example? Or is that not a particularly promising research direction?
Oh, that is a very good point. And yeah, I mean, we haven't done that yet, but this is actually a very cool idea, and this can be actually very easily doable when you are running, because you know the underlying hardware. At least even if you don't have enough time to do a thorough benchmarking and get the exact concurrency values of the devices, by knowing little bit of the devices. And most of these SSDs, they have this smart technology which kind of holds all the information of the devices, like the number of channels, number of writes that has been performed, number of erases, and so on and so on. It keeps track of a lot of statistics and everything. So yeah, by getting that, it can be, I mean, you can get that ballpark value, and you can actually seamlessly switch between devices if required in such cloud environment. But yeah, it is actually a cool idea and can be a very good extension when using this concept.
Awesome, cool. So, Papon, what impact do you think this work can have then? Like, as I know, as a software developer, a data engineer, or one of these types of jobs, how do you think they could leverage your findings in their sort of day-to-day working life?
Yeah, like the key takeaway, like when you are using or when you are developing systems for SSDs, try to keep in mind the differences between hard disks and SSDs, like the read rate asymmetry and access concurrency. If you keep in mind that, yeah, we have this property, so how can we exploit these properties, or how can we get the most out of these devices? Can we do concurrent IO, and how many IOs can we perform? If you go beyond your limit, that will hurt your performance. So these are essentially the questions that you sort of kind of keep in mind, and then design systems that are better tailored for these kind of situations.
Yeah, I think that's really good advice. Sort of be aware that of the hardware you're running on, right? And sort of like, how can you exploit those characteristics to kind of to make whatever it is you're building more performant, right? That's really cool. I mean, how long have you been working on this ACE project? And kind of following on from that, what's the most interesting sort of lesson you've sort of learned whilst on that journey?
Yeah, that is a good question. So I started working on ACE in like late 2020s, and we kind of finished it last year. So it was like 1.5 year, or maybe something around Yeah, I think 1.5 year of project, but during that time we got to actually. This is not like the only contribution of our work. We previously also published a Damon paper and a Cider paper based on these characteristics of modern storage devices. So we got to learn about SSD concurrency, how they are different, and read-write asymmetry, how to measure them. We developed a tool to actually do this benchmarking, and then we kind of analytically did a study that how the systems that can actually batch writes and can, if they can perform those batch writes concurrently, how will be the performance improvement. We model this, and so on. And during the development of ACE, we got to learn these cool things about SSDs. Like, for example, Smart is one of them. You get to know these very cool stats of the devices. Like, one of our reviewers asked the impact of SSD endurance, and we kind of had to perform an experiment that shows the number of writes of the devices, and it does not increase. So I got to learn that all these devices have these statistics in the flash controller, and you can access them, and you get to know about this. So there is like, narrowing down to one lesson will be very difficult, but I think these small learnings about different devices and the different buffer pool managers, the state of the art systems, you get to learn about them, what research has been done. And yeah, I mean, narrowing down to one lesson will be difficult.
No, that's okay. You can have many lessons. That's the more lessons, the better, right? I mean, that's good. Were there
Yeah.
any sort of dead ends like along the way, like any things you tried that sort of failed, or you're like, oh damn, we need to change this now, or yeah, I guess was it just one big sort of upward trajectory
Oh,
throughout the
no, no, no. No, definitely not. So, as I said, that we kind of started it in 2020, and we almost had a working buffer pool. That was a prototype, so it was not implemented in Postgres. So we had it running in 2021. We went down, and but the key idea more or less remained the same. But there has been a lot of optimizations, like the refactored design space that was not previously there. So previously, the main idea was just to write multiple pages whenever possible and see what happens with that, and like separating the eviction from the write back, that was not initially there. And yeah, we got some very good reviews from the reviewers. They asked us to suggested us to implement it in a real system, and also how we can actually, if we can actually use prefetcher and so on. So we got some very good ideas and feedbacks from the reviewers, and we started implementing those ideas, and then we moved on to implementing it in the Postgres. So yeah, it has actually changed a little bit over time, but not too much. But the buffer pool that was like 2 years ago, and the buffer pool that we have now, the performance is drastically different, because like by the refactoring and also adding some optimizations in the code, this actually impacted a lot over time.
I guess is this your main sort of project you've been working on? I guess my question here is, what other things are you working on at the moment? Can you tell the listener about your other research?
Yeah, so I work a little bit on LSM. So we have with Shubhadeep, we worked on Lithi. So the Lithi is an delete our LSM engine. So I contributed in one of the implementational aspects of Lithi. So I do a little bit of LSM stuff, and one of my other big projects is actually, we call it relational memory. So the idea of relational memory is a software hardware co-design space where you use the concept of hardware specialization, and you use specialized hardware like FPGA. So our key idea is that have we have a we have a row store, and how we can actually access its different columns without accessing unnecessary data from like in the cache line. So can we actually do it? And we have built a prototype. We call it relational memory, and it can actually using a custom FPGA-based hardware, we built the first prototype, and on a PSPL platform, we experimented that, and we are seeing that you can actually perform faster than the DRAM. It can be faster than the DRAM in some cases, and for some analytical queries, it can be as fast as the DRAM. It can provide comparative performance. So that is actually very cool work that we have been working on. Now we are trying to extend this idea of relational memory to the memory controller, and also we have been thinking about making this a concept more general, not keeping it specific to database systems. Rather, we are working now on a data reorganization unit that can benefit any sort of data systems like tensors or matrix operations or image processing and that sort of stuff. So you can essentially you can accelerate any operation that involves a set of data or involves transforming data from one shape to another shape.
Working on some really cool things there. So, I mean, I really like this question. My favorite question, and it's like, can you tell me more about your creative process? How do you go about sort of generating ideas and then selecting, this is something that I'm going to spend the next 2 to 3 years maybe working on? Like, how do you go about doing that?
So I can tell you how we started this project. And so the main idea of this project was actually this is Manos's brainchild, and Manos had this idea of developing asymmetry and concurrency, our Bufferpool. So he shared several ideas with me, and one of them was this concept of developing better data systems for considering the asymmetry and concurrency of devices. And I kind of liked the idea because I honestly I don't really know, but for some reason it intrigued me, and that probably one of the reasons I have always kind of had a soft corner for hardware. Like during my bachelor's, I worked a lot on hardwares and stuff. So when I got to know that there were some projects related to storage devices and also like the relational memory that is also FPGA based and hardware based. So that probably intrigued me. I don't really know. And now, if I want to talk about like the idea generation process or like the whole process of developing a system, like what I always want to do is that like to get the solution of a problem, you need to understand the problem well, and you also need to understand the problem from different perspectives. Like you can solve a problem from many different ways, like in multiple angles it can be done. So if you have the good idea of these different angles, then try to think like which angle can you can actually get a solution from there. So like if you know all the perspective, and then you get to have some sort of intuition in one of these perspectives that maybe if we tweak this, then something can happen. Do some pen and paper work, see if it is actually viable, and then the next step is essentially testing your idea and build a prototype. So I mean the first prototype that should work well for, let's say, 1 to 1000 nodes. And after you have a working prototype that kind of supports your hypothesis, and then you can start working on optimizing it and maybe adding more features or more probably better designs and so on and so on. So these two steps actually have like it is not like it does not happen in one iteration. There will be some back and forth between developing the prototype. As you work more and more towards your idea, you develop better understanding of the whole system and a whole process, and you get more ideas. And I guess that's it.
No, that's a fantastic answer to that question. Like I say, it's really intriguing to see how everyone works, because there's so much like the disparity in answers across that question is fantastic. Just to see how everyone's got their own little way of doing things is great. But no, that's really cool. Yeah, so just a couple more questions now, Papon. So the first one is what do you think is the biggest challenge in databases, data management, research today?
Oh, wow, that this is a very like big question, and
Yeah, very big picture.
again, I don't think I can pinpoint to one problem, but maybe like handling the like the different types of data, and the data are now being generated from many sources, like from different sources and different varieties of data. With this exponential growth of data that is being generated from different sources, like handling this large amount of data is a challenge. So there has been a lot of work that is being going on with like indexing. Learned indexes is a cool thing, and like developing good key value store that supports good concurrency control, transaction management. So all these are actually important, and also like with the new privacy regulations coming in place, so privacy is a big thing. And the like with machine learning, many people are using many machine learning concepts to accelerate many like small components of data management system, which is also a very cool way of doing things, like or especially like auto tuning, or robust workload or robust system design based on workload uncertainty, and so on and so on. So uh, yeah, I mean, pinpointing it to one thing will be different. I guess I have already listed 10 challenges or so on and so on. So a lot of stuff are happening, but I think handling this large amount of data from variety of sources while ensuring the privacy, I think, yeah, that can summarize the whole thing.
Yeah, that sounds great. Plenty of interesting research left out there for us all to do, right? So yeah, cool. Okay, there's time for the last word now. So, what's the one takeaway you want the listener to get from this podcast today?
Know your SSD, know your storage device, know the characteristics of the device, and while you are designing the systems, make sure that you keep into account those properties and tune your system to that to get the most out of your device.
Fantastic. Let's end it there then. So thanks so much, Papon, for coming on the show. It's been a fantastic conversation. I've really enjoyed it. If the listener is interested in knowing more about Papon's work, we'll put a link to everything in the show notes so you can go and find that. And again, if you enjoy the show, please consider supporting us through Buy Me a Coffee, and we'll see you next time for some more awesome computer science research.